Hello, I'm Jim Burnett, and during this episode of our series, The Airplane and NASA, we're examining how NASA works to improve aircraft performance and safety. The first segment in this program concentrates on airflow and turbulence and the effects on aircraft.
NASA is using powerful new technologies to better understand the role of flow phenomena in flight. Primarily computer-related, these new methods promise to transform the development of new aircraft. Flow takes many forms. In a NASA water tunnel, vortex flow around a wingtip is illustrated with lasers. Researchers have been tracking flow since the first wind tunnels. Boundary layer, where flowing air meets an aircraft body, is measured in 1 molecule thickness. The question is how gas molecules move over airfoils to produce better flight. Insights into the principles of flow by early aerodynamic engineers created the powerless glider. The glider is a pure example of basics of airfoils that create lift and flight. Flow has been measured in a variety of ways. NASA scientists use smoke generators to chart wingtip vortices from large aircraft. These sometimes cause problems for other aircraft during takeoffs and landings. Scientists are also using brand new holographic interferometry to show pressure cells around an aerodynamic body. But the latest technology, called computational fluid dynamics, uses supercomputers able to do 1 billion calculations per second. At NASA Ames by 1986, a supercomputer will provide scientists with exact modeling of flow. The system will have a memory of 64 million computer words. Its 1 billion floating point calculations per second, known as a gigaflop, allow flow calculations at a myriad of points in a 3-dimensional matrix around an aerodynamic body. Computer graphics generated by the coming supercomputers will illustrate flow in a way never available to researchers before. The computer can show rocket scientists the sonic surface in 3 dimensions on a proposed body design. A sonic surface is the area where air passes from subsonic to supersonic speeds. Computer graphics can show the scientists the same airflow in terms of pressure gradients. Here, computers illustrate flow separation on a wing so engineers can design turbulence out of a proposed airfoil. And computer graphics clearly show the interference flow effects on the exterior surfaces of a wing and fuselage. By this method, scientists can see and understand the interactions of shock wave and boundary layer in a proposed aircraft design. Using super-fast new computers, scientists can sort out better designs from good designs and eliminate a large part of the former expensive wind tunnel experiments. Really promising designs are identified by a computer and then taken to a NASA wind tunnel for testing. In these wind tunnels, computer predictions can be verified. Next, a decision can be made to go forward with an actual aircraft. One of the chief proponents of this new method is William Ballhaus, the new director of NASA Ames, who used the computer to design the most maneuverable airplane yet, called HIMAT. HIMAT is a technology demonstration aircraft. It has flown, but only as a remotely piloted vehicle because flying near supersonic speeds it can pull 8 Gs. So strong, Ballhaus and others are not even certain a man could pilot it. HIMAT allows tests of the interactions of several new design ideas. It uses composite materials. The wings and canard are aeroelastically tailored for stability, and it employs digital control systems. The success of HIMAT proves computational fluid dynamics will vastly improve safety, speed, and efficiency for every type of aircraft in tomorrow's aviation.
NASA is experimenting with fascinating wing and propeller designs that are expected to lead to faster, more economical aircraft.
NASA Aeronautics is flying into the future aboard some strange-looking aircraft designs. The oblique wing airplane looks like a flying scissors, but it promises high speed, low noise, and better fuel efficiency. The X-29A seems to have its wings on backwards, but the forward-swept wing concept is the newest idea in high-speed fighters. A concept called joined wing gives promise for high strength and low weight through its triangular truss design. And NASA designers are bringing back the propeller in a striking new swept-back look to capture high speed and fuel efficiency. The X-29A offers high speed and high maneuverability. NASA is using computer graphics to generate designs of aircraft like the X-29A. Model flies on a tether at a NASA wind tunnel. And finally, a small scale model is sent into the sky to prove it flies. The rapid advances of such designs as the radical forward-swept wing X-29A are made possible by large-scale wind tunnels, such as the new National Transonic facility at Langley Research Center in Virginia. At the National Full-Scale Aerodynamics Complex at NASA Ames, some of the early supersonic transport designs were tested. Progress includes this advanced supersonic fighter concept at Langley Research Center and the F-16XL. Its double delta wing increases maneuverability, fuel volume, and supersonic cruise performance. But the ultimate is the HIMAT test airplane, the first wing designed entirely by computer. Computer projected flight characteristics were later verified in NASA wind tunnels and finally in remotely piloted test. It flies at Mach 2 with twice the maneuverability of any other aircraft. Future concepts like the joined wing promise a lighter and more fuel-efficient commercial aircraft. Other new approaches, like this supercritical wing on a Learjet model, are in NASA's wind tunnels now. The next effort is to design a new generation of transport aircraft. Wind tunnel testing shows their new propellers provide near-jet speeds while using 25% less fuel. NASA Lewis engineer Bob Jiraki.
It's a very unusual structure, a very unusual propulsion system, and we are trying to develop confidence in the commercial industry that this is a viable propulsion system and it can be designed reliably. And when you build a full-scale one, you can be confident of the performance and structural design.
Also being looked at for extended flights such as New York to Hong Kong around the year 2000 are hypersonic transports. Hydrogen-fueled, these aircraft will fly up to Mach 6 or 4,000 miles per hour at altitudes above 60,000 feet. In the search for a viable bread-and-butter supersonic transport, NASA is looking at the oblique wing aircraft. Internationally known aviation innovator R.T. Jones first proposed oblique wing aircraft 30 years ago, but put the idea aside. Now the oblique wing may offer the best of both worlds. With a movable wing out straight, the aircraft can fly at low speeds and low noise over populated areas. With the wing scissored almost parallel to the aircraft body, it can fly as fast as Mach 1.4 or 1,000 miles per hour with great fuel efficiency. The design may turn out to be the supersonic transport which doesn't burden its owners with high costs. At Ames Dryden Flight Research Facility in the high desert near Edwards, California, NASA is now preparing to fly the oblique wing supersonic for the first time by mounting it on an F-8 fighter. Preliminary design studies for the commercial transport version of the oblique wing are seen here. Such exotic advanced designs as the oblique wing will push forward U.S. aeronautical progress.
NASA scientists are researching new material combinations that can be used for aircraft construction. The goal is to produce lightweight structures that save fuel, yet are durable enough to provide long life service.
Now the challenge is to design aircraft structures which use the basic strengths of the new lightweight materials to shield passengers from the potentially disastrous forces of a crash. This new material is a composite of graphite fibers impregnated with chemicals called polyamides, a class of plastic resistant to high temperature which also have high tensile strength. Dr. Norman Johnson, Senior Scientist, NASA Langley.
Of all of the fibers that we use today for building composite materials, graphite fibers offer the best all-around properties. Graphite composites are lighter, stiffer, and stronger and will not expand when heated or contract when cooled.
Langley researchers have subjected components made with these materials to a variety of destruction tests. Cylinders made of the graphite epoxy and fiberglass were compared in the ultimate test, total destruction. The crash test of an aircraft section helps design a cabin structure because it predicts how the structure will deform on impact. This is extremely important in rotorcraft research, as helicopters must be designed for hard autorotation landings. Using cameras mounted inside a test vehicle, engineers can see how passengers would be affected in a crash and whether the impact would be survivable. Langley Research Center in Hampton, Virginia routinely subjects airframes to powered crashes to examine how new ideas in construction complement the strengths of the new graphite epoxy and other advanced materials. Graphite epoxy and other composites are another technology for proposed fuel-efficient transports. These airplanes achieve their primary savings through the use of a new propeller design, but new materials will reduce aircraft weight by as much as 15%, a significant savings in operating cost. NASA laboratory research and design work is continuing with graphite epoxy and a range of other composite materials, such as new aluminum alloys created by powder metallurgy and various metal-plastic combinations. All these materials promise higher strength and lower weight. There is at least one plastic airplane now flying. That is the Lear fan, now receiving its operational certifications.
Like a gifted musician, an aircraft pilot can improve performance through practice. The NASA simulator provides that experience on the ground.
NASA is trying to build safe operation, landing, takeoffs, maneuvers into every aircraft that rolls off the design boards and down the runway. The new tools in this effort are advanced flight simulators, which can screech through various violent maneuvers without ever leaving the ground. Large-scale computers supply the real motions in response to pilot moves, as well as real views out the cockpit window. NASA has several major flight simulators with huge motion generators, which simulate actual flight maneuvers. By using these simulators, aeronautical engineers are better able to predict the design limitations of new aircraft, to predict that an experienced pilot will be able to take to the skies and return safely to the ground again using video landing displays, which are so close to real airports, it's hard to tell the difference. The NASA simulators have helped test and improve the handling qualities of the space shuttle and test impossible on a mission. Here, a shuttle pilot brings her in.
So after descending some 900,000 feet and slowing from essentially Mach 25 down to Mach 0.5 now, we have the last 10,000 feet of the descent to do, and lowering the landing gear. Okay, about 10 feet in the air now. All we do is let it land itself. There's main gear touchdown, speed brake's coming out. We're derotating. Nose on the ground, steering's on, and we can get on the brakes.
But the real purpose of the simulator is to test aircraft design against the abilities of real pilots. At NASA Ames in California, the vertical motion simulator provides the high-fidelity simulation of flight motions engineers need. A large computer instantaneously translates the control commands from the pilot into motion of the simulator cab. The VMS can rise or fall 60 feet. It can pitch, roll, or yaw and travel 40 feet horizontally. Through the use of the vertical motion simulator, a pilot can try hundreds of maneuvers repeatedly to be certain that the aircraft design being tested will proceed through the planning and testing process to finally become a flyable plane. And a mock-up of terrain and landing strips is simultaneously photographed by a moving camera which flies over the scene and is televised onto a screen, vividly simulating the pilot's view out the cockpit window. Another of the high-fidelity NASA simulators is the flight simulator for advanced aircraft, which can provide the wide horizontal motions of very large transport aircraft, such as the Boeing 747. It has been used to establish design criteria for such aircraft as the Concorde SST, because it can test the ability of a pilot to control an advanced aircraft when an unexpected system failure occurs. Here, the computer gives the pilot a potentially disastrous engine flameout. The pilot rapidly regained control, proving the design is flyable. These big simulators do not train pilots, they provide aircraft design information. Another important tool for the development of control systems is this heads-up display simulator. Heads-up display allows the pilot to keep his attention on the outside view while important instrumentation is superimposed on his window. Another simulator assists engineers to design display systems which will improve a pilot's ability to fly the aircraft in poor weather conditions. In this simulation, a pilot brings a helicopter in for a landing on a Navy destroyer. NASA is also working to design a helicopter radar landing system, which could be of great use by pilots in locating small sites such as oil platforms at night or in bad weather. NASA simulators are using state-of-the-art technology and cutting-edge science to help ensure flight safety in the future.
Air safety is a prime concern at NASA. This next segment shows how NASA with the FAA and the airline industry are working to improve air safety.
Americans depend on safe air travel. The Aviation Safety Reporting System gathers information never before available in cooperation with the FAA, the major airlines, and NASA Ames Research Center. NASA's William Renard heads the program.
We have a very safe aviation system, but it's very complex. Pilots bust altitudes, controllers sometimes don't brief other controllers properly. Aeronautical charts sometimes are printed inaccurately. The fact of the matter is there are a lot more incidents than accidents in our system. The Aviation Safety Reporting System is designed to provide a place that pilots and controllers can report these safety issues. We can analyze that data, turn it around, and make safety improvements to the system. In the 8 years we've been in existence, we've received 37,000 reports of incidents in the aviation system. What we've been able to do is to take that information and turn it around, give it to the system people, the Federal Aviation Administration, the National Transportation Safety Board, the Department of Defense, and use the data to improve the system. One of the methods we use is the callback publication. It's a publication designed to convey safety information to pilots and controllers directly. What kind of issues are we seeing, and what are we doing about it? The nice thing about the Aviation Safety Reporting System is the fact that it's confidential. People can report to us without fear of enforcement action, but the safety issues are still discovered and acted upon.
In an entirely different way of researching safety, NASA studies case histories of actual crashes. It is important to reconstruct the accident to see what happened so it does not happen again. This is a computer-generated graphic of an actual case history, exact in every detail of what occurred when this aircraft crashed. Factual data are taken from the reports of the federal agencies that investigate it. 38,000 reports are on file with the Aviation Safety Reporting System. The majority of air disasters are due to human error. That's why NASA built the new Manned Vehicle Systems Research Facility at Ames Research Center, Mountain View, California. This facility contains all the elements needed to accurately recreate flight scenarios. In this safety laboratory, an FAA off-duty flight controller issues instructions to the pilot in the simulator exactly as he would on duty. Commercial pilots are asked to participate as the voices of other pilots in the air traffic system. And the researcher interjects a surprise element in what might have been a routine flight, an element often taken from an actual case report. In this case, the pilots buckle up and go through takeoff procedure. They know something unusual will happen to them during this flight, but they do not know what it will be. Out the cockpit window, they see a high-resolution closed-circuit television picture generated by a large computer, which responds to every control movement they make in the cockpit. They roll down the runway and lift off into the night sky. The simulator moves instantaneously on commands from the computer, which has gotten its cues from the pilot's controls. It is this motion which gives the pilots the realistic feeling of flying the airplane, the Boeing 727. In the cockpit, it is a routine flight. But nearby in the experimenter station, a researcher decides to induce a problem, carefully prepared from the Aviation Reporting System's case studies. For the flight crew, the waiting game is suddenly over. The pilot sees a flashing alarm light that indicates they have a fire in engine 2. In this case, the simulator flight crew did exactly as they were supposed to, and the fire was quickly extinguished. But the pilots aren't out of it yet. They still have to bring the aircraft around for an emergency approach and landing. When they put the airliner back on the runway safely, they have correctly solved a problem which gave another pilot bad dreams. This NASA recreation of the entire commercial aircraft operating system ensures that the advanced aircraft of tomorrow continue to fly with safety first.
In other aeronautic research, work continues to address hazards such as fire, lightning, spin, and air turbulence.
The hazards of aviation are under continuing study at NASA research centers. The prevention and countermeasures of aircraft fires, the effects of lightning storms on aircraft which are struck while in flight, a phenomena encountered at some time on almost every aircraft route, as well as methods to counteract the often disastrous syndrome of stall and spin, which is a major hazard of flight for small general aviation aircraft, and which is very difficult for pilots to control and conquer. Researchers also study clear air turbulence, which often occurs on the eastern slope of the Rocky Mountains, where air movements from the west roll over the peaks and generate dangerous cylinders of extremely fast-moving and turbulent air that can cause pilots to lose control of large and small aircraft. By far the most frightening and dramatic hazard to aircraft is fire. NASA researchers are developing fire-resistant wall panels, windows, and insulation. Recently, these studies produced a fire-resistant envelope to wrap polyurethane seat cushions and retard the propagation of the toxic smoke, which often causes more injuries and fatalities than fire itself. NASA researchers are burning up aircraft in order to study ways for flight crews and passengers to gain a few moments of reaction time to save themselves should they find themselves in what experts call a flaming fuel environment. The Chemical Research Project's office at NASA Ames in California recently showed that experimental window materials were able to withstand external flaming fuel environments longer than conventional materials. This will add to the time passengers will have to act to save their own lives. NASA researchers have also developed improvements in aircraft fuselage construction, which could buy passengers more time to escape a fire. In this comparison test, an unprotected section of a fuselage is destroyed, while an adjacent section built with fire-resistant techniques appears to be the sort of aircraft you would want to be in if a fire were to break out. It successfully resisted the flames. A family of additional fire-retardant materials is under study at NASA laboratories. Another significant hazard to pilots is stall and spin, in which the aircraft wing loses its ability to provide lift, resulting in an uncontrollable spin fatal 15% of the time. At a California airstrip, model airplanes are set up to fight stall and spin, while across the country at Langley Research Center, design proposals are tested in a vertical wind tunnel. And NASA pilots also take to the air and test aircraft to try to induce stall and spin. Langley pilot Jim Patton.
I believe strongly that the work we're doing will influence future airplane designs, and has influenced already in some cases, those designs to make airplanes safer to fly. And it will decrease the number of fatalities that would otherwise have existed.
Clear air turbulence is another major concern to pilots in NASA Aeronautics. It is a hazard which occurs when winds rolling over mountains produce adjacent eddies of clear but highly turbulent air. In the United States, the problem occurs most often on the eastern slopes of the Sierra Nevada and Rocky Mountains as air masses move in off the Pacific. These fast-moving weather systems can lurk unseen for an unsuspecting pilot, and NASA researchers are studying methods for predicting and avoiding areas where clear air turbulence occurs. NASA Langley Research Center, Hampton, Virginia, flies a special F-106 fighter into the worst weather available to study another problem. Pilot Perry Deal and associate Bruce Fisher are going up to be hit by lightning. The F-106 is well suited for this mission because its all-metal construction makes it lightning-proof. Within moments of takeoff, the fighter is in the thick of a storm. Pilot Deal is looking for the worst lightning and turbulence he can find in order to take lightning hits and send information back to the researchers recording flight data on the ground.
Another direct strike, still heavy rain. And this is the heaviest turbulence I've flown in 3 years.
The challenge now is for NASA to incorporate what they have learned from the lightning flights of Perry Deal and Bruce Fisher and the F-106 into a new generation of aircraft. NASA is studying fire, dangerous weather systems, and lightning, as well as other operating problems, to make certain that aviation continues its excellent record of passenger safety as a new generation of aircraft flies toward tomorrow.
Since its founding in 1958, NASA has been providing the technology for improving the efficiency and quality of aircraft performance. Using computer technology, physical sciences, testing, and human ingenuity, NASA continues to help make aircraft safer, faster, and more economical. I'm Jim Burnett at NASA Lewis Research Center.